Welcome back, everyone. Ready to dive into some more fascinating math? Today we'll be exploring tropical arithmetic, and I've got to say, looking at the source material here, it really seems to turn everything we think we know about math on its head.
It definitely challenges our intuitions.
I mean, get this, addition becomes finding the minimum,
Yeah.
and multiplication, well, it stays addition.
It's definitely different, but that's part of what makes it interesting.
Absolutely, and it's got all these implications for different fields.
From algebraic geometry to computer science, even.
Yeah, so right away I'm looking at these basic operations,
Uh-huh.
and I'm struck by just how simple they seem.
Okay.
In the source material, there are these addition and multiplication tables.
Right.
And honestly, they look like something you'd see in, like, elementary school.
Really?
3 plus 7 equals 3. 2 times 5 equals 7.
Wow.
It's almost like deceptively straightforward.
Well, the simplicity of the operations is definitely intriguing,
Yeah.
but it's important to remember that we're working within a different algebraic structure here, a semiring,
Okay, a semiring.
and that has some important consequences.
I see.
One of the key differences, for example, is that in tropical arithmetic, there's no subtraction operation.
Okay, so no subtraction allowed.
Right.
That makes me wonder, how do you solve equations then?
That's a great question.
Like, what happens to something like 4 plus x equals 13 in this system?
That's a really good question, and it actually highlights a very fundamental difference between classical and tropical arithmetic. In tropical arithmetic, that equation would actually have no solution.
No solution.
No solution because we don't have additive inverses.
Oh, I see.
We can't just undo addition to isolate x.
So the lack of subtraction really changes how you approach problem solving.
Absolutely.
It's not just swapping out symbols. It's a whole different way of thinking about equations.
Exactly. It's a different way of thinking about solutions, too.
Now, the source material mentions that even without subtraction, tropical arithmetic is used in some pretty practical applications.
It is, yeah.
It mentions things like dynamic programming and finding the shortest paths in graphs.
Right.
So how can this seemingly simple system handle such complex problems?
Well, let's take the example of finding the shortest path between 2 points in a network.
Okay.
You can imagine that network as a graph with nodes and edges,
Yeah.
where each edge has a weight representing distance or cost.
Mm-hmm.
Now, picture a matrix that captures all those edge weights.
Okay.
When we perform tropical matrix multiplication on this matrix,
Yeah.
something really interesting happens.
I'm looking at it here, and it says the resulting matrix actually encodes the shortest paths between all pairs of nodes.
Exactly.
It's like this tropical operation elegantly simplifies a complex problem.
It does.
Wow.
The minimum operation in tropical arithmetic naturally selects the shortest path,
It makes sense.
making it perfect for this type of problem.
Okay.
And that same principle extends to dynamic programming,
Right.
where you break down complex problems into smaller overlapping subproblems.
So tropical arithmetic gives us a really powerful framework for tackling these optimization problems.
It does?
In all kinds of fields, that's
Yeah.
amazing.
Yeah.
Now, there's this other term in the source material that I found interesting.
Okay.
Tropicalization.
Mhm.
Kind of sounds like giving regular math like a tropical makeover.
You could say that.
What exactly does this process involve?
Tropicalization is basically a way to connect classical and tropical arithmetic.
Okay.
It involves taking a limit.
A limit.
As a small positive number, usually called epsilon, approaches 0.
So epsilon goes to 0.
Right.
And this process turns our regular arithmetic operations
Yeah.
into their tropical counterparts.
Exactly.
It's like we're looking at regular math through this epsilon goes to 0 lens, and we're seeing this hidden tropical layer.
That's a great way to think about it.
It sounds very cool.
It allows us to explore those connections between these two seemingly very different worlds.
Right.
And we can uncover these surprising relationships and insights.
And this isn't limited to just basic arithmetic, is it?
No, it's not.
It extends to more complex things like polynomials.
It does.
Speaking of polynomials, the source material mentions that tropical polynomials have this very unique connection to their graphs.
They do.
It seems like their roots are revealed in a really visual way.
They are.
So how does that work?
Well, the graph of a tropical polynomial shows its roots as breakpoints.
Breakpoints.
Points where the graph changes direction.
I see.
And those breakpoints directly correspond to the polynomial's roots.
So we can just see the roots of a polynomial
Yes.
just by looking at its graph.
Exactly. The graph becomes like a visual map of the polynomial's solutions.
That's incredible. And it even says here that the fundamental theorem of algebra holds true in the tropical world.
It does.
So does that mean every tropical polynomial can be factored?
Yes, it does.
Just like a regular polynomial?
Right. The fundamental theorem of algebra in the tropical world says that every tropical polynomial can be uniquely factored into linear factors.
Wow.
It really highlights those deep connections between these two worlds.
Hold on, though, because the notes also mention this counterexample with a polynomial
Yeah.
that has two variables, and it seems like the unique factorization breaks down.
Right.
If the theorem is true, how is that possible?
You're right to point that out. There's a nuance there.
Okay.
Unique factorization applies to the tropical polynomial functions,
Uh-huh.
not the expressions themselves.
Okay.
You can have multiple expressions that represent the same function, even if they look different.
So it's not just about the form of the polynomial.
Right.
It's really about the underlying function.
Exactly.
That makes sense.
Good.
Now, this reminds me of regular algebra, where we use polynomials to represent shapes. Can we do that same thing with tropical polynomials?
Yes, you can.
Is there something like tropical geometry?
You're exactly right, and that's where tropical curves come into play.
Tropical curves.
These curves are defined by tropical polynomials,
I see.
and they give us a geometric way to understand these seemingly abstract expressions.
So we can visualize tropical polynomials as shapes.
Yes, you can.
That's really interesting.
It is.
Can you give me an example of what one of these tropical curves might look like?
Sure, let's consider a tropical line in a plane.
Okay.
Visually, it's represented by 3 half-rays,
3 half-rays.
all coming out from a central point.
Wow.
It's very different from our usual idea of a straight line.
It is. It sounds a lot more intricate.
It is.
So even these basic shapes look totally different in the tropical world.
Yeah.
It makes me wonder what other geometric surprises are out there.
There are many.
Like what?
For example, in classical geometry, 2 lines might intersect at one point,
Right.
or be parallel.
Or even be the same line.
Exactly. But in tropical geometry, 2 tropical lines always intersect at one point.
Always.
Always. That's one of the really intriguing things about tropical geometry.
Wow, that's mind-bending.
It is.
I'm already seeing how tropical geometry can really challenge our ideas about geometry
It does.
and lead to all sorts of new insights.
It does. So we've talked about these tropical curves.
Yeah.
And how they're defined by tropical polynomials.
Right.
But how do we actually picture them?
I'm picturing something pretty different from like the smooth curves you see in regular geometry.
Yeah.
The source material kind of hints at something more complicated,
Okay.
almost like a network or paths or something.
You're on the right track.
Okay.
Think of a tropical curve as a bunch of line segments.
Yeah.
Each one representing a term in the tropical polynomial.
Okay.
And the slopes of these segments are determined by the exponents in those terms.
Right.
And the points where they intersect, those represent the breakpoints.
The breakpoints, the
Roots
roots.
on the polynomial.
So it's like the structure of the curve is a direct reflection of the polynomial itself.
Exactly.
Like a visual code.
Yeah.
And this helps us analyze and solve problems.
It does.
Like, remember we were talking about how tropical arithmetic can be used to find shortest paths?
Right.
Well, it seems like tropical curves can actually show us those solutions visually.
They can.
That's amazing.
Instead of just calculating it,
Yeah.
we can actually see the solution
Laid out geometrically.
as a tropical curve.
So cool. It's like connecting those abstract calculations to an actual image.
Yeah, and each segment in the tropical curve
Right.
represents the cost of going along that path in the network.
Oh, I see.
So we can actually see the cost right there in the image.
So we've been talking about tropical arithmetic and geometry as separate things,
We have.
but I feel like there's this deep connection between them,
There is?
like two sides of the same coin or something.
That's a great way to put it.
And I think that connection has to be this tropicalization thing.
It is.
We talked about how it bridges classical and tropical arithmetic,
Right.
but it seems like it goes even further than that.
It does, yeah.
We can tropicalize not just numbers and operations, but also matrices
Yeah.
and even entire algebraic varieties.
That's right.
So we can take something like a classical algebraic variety, which is basically a geometric object defined by polynomial equations,
Yeah.
and find its tropical counterpart.
Exactly.
It's like translating geometry into the language of tropical math.
That's a great way to think about it.
And the amazing thing is,
that?
it says here that a lot of the important properties of the original variety
Yeah.
are actually preserved,
They are.
even after tropicalization.
So even though the objects themselves might look different,
Yeah.
their essential characteristics stay the same.
It's like looking at a blueprint
Uh-huh.
of the original.
Through a tropical lens.
Exactly. So cool.
But here's where things get even more interesting.
Okay.
Some properties are preserved,
Right.
but others change in really cool ways.
In the tropical world.
Yeah, for example, the way curves intersect can be really different.
Different from classical geometry.
Yeah, and this leads to some new insights.
So it's not just a straightforward translation then.
It's not.
There's this like interplay between the two worlds.
There is.
With properties changing and evolving as we move between them.
Yeah, it's like we're exploring a whole new mathematical landscape.
With its own set of rules.
And patterns, exactly.
And these patterns can show us hidden structures in those original algebraic objects.
They can.
Wow, this is fascinating stuff.
It is.
But I am curious about the practical side of things.
Okay.
Are there any real-world examples where tropical geometry has been used?
There are.
Like what?
One really interesting example is in phylogenetic analysis.
Phylogenetic analysis. What is that?
It's basically trying to understand evolutionary relationships between different species.
Oh, okay.
And it turns out you can represent these evolutionary trees as tropical curves.
Yes, tropical curves. Wow.
And this allows researchers to use the tools of tropical geometry to analyze these different evolutionary hypotheses.
So we're using tropical curves to trace the branches of the tree of life.
Yeah, it's really cool.
Discovering this hidden geometry within evolution.
Exactly.
That's incredible.
And another area where it's being used is in optimization and operations research.
Okay.
A lot of real-world problems, like scheduling and network design, can be thought of as optimization problems.
Okay.
And tropical geometry can help us solve those.
It's like tropical geometry is this super versatile tool.
It is.
Connecting abstract math to real-world problems.
Absolutely. And its versatility comes from the fact that it can give us this visual and often simplified representation of complex problems.
Making them easier to work with.
Exactly.
Now, you mentioned earlier that we can tropicalize not just numbers and polynomials, but entire algebraic varieties.
That's right.
What can we learn by studying the tropical varieties?
By studying tropical varieties, we can get a better understanding of the geometric and combinatorial properties of the original varieties. And the cool thing is that tropicalization often simplifies the problem.
Oh, that's good.
Making it easier to analyze.
It's like we're taking these complex geometric objects and putting them into a language that's easier to understand.
That's a great way to think about it.
And we might see patterns that we wouldn't have seen before.
Exactly.
Wow.
And those patterns can often be linked back to the original variety.
That's amazing.
Giving us a much deeper understanding.
This is really remarkable stuff.
It is.
I'm starting to really appreciate how powerful tropical geometry is.
Yeah.
It's like unlocking this hidden layer of structure within algebra and geometry.
That's a good way to think about it.
And as we go deeper,
I'm
sure we'll find even more connections and cool concepts.
We will.
But before we move on,
I
think it's worth taking a moment to appreciate what we've seen so far. This tropical mathematics. With its unusual operations and visuals. It's really challenged my assumptions about math.
It's really expanded our horizons.
Yeah.
It has. It shows us the power of looking at things from a new perspective.
Right.
It reveals connections and possibilities we might never have considered.
I can't wait to see where else this leads us.
I know, me too.
Right.
Now let's move on to another interesting area.
Okay.
Tropical linear spaces.
Tropical linear spaces, huh?
Yeah.
I know in regular math, linear spaces are like lines and planes.
Right.
And all those higher dimensional spaces.
Yeah.
What happens when those spaces become tropical?
Well, just like tropical curves gave us a new way to look at polynomials.
Yeah.
Tropical linear spaces kind of connect linear algebra with tropical geometry.
Okay.
They come from systems of linear equations, just like in classical math.
Okay.
But their geometric structure is pretty unique.
So we're still dealing with systems of equations and stuff.
Right.
But I bet the solutions look way different.
They do.
In the tropical world.
In classical linear spaces, they're smooth, like lines and planes.
Right. Flat.
But tropical linear spaces can be more complicated.
Okay.
They can have corners, bends.
Oh, what?
They're like piecewise linear objects.
So the tropical world makes these spaces more geometrically complex.
You could say that.
Does that make them harder to analyze?
Not really. These geometric features actually tell us a lot about the equations.
Oh.
They give us a visual way to understand their properties.
So it's like those breakpoints in the polynomials.
Exactly.
They give us information.
And just like tropical curves, tropical linear spaces have applications in lots of fields.
The source material mentions phylogenetic trees.
Right.
Those diagrams that show evolutionary relationships.
Exactly.
How do tropical linear spaces come into play there?
Well, the space of all possible evolutionary trees can actually be represented as a tropical linear space.
Ah, really?
Yeah, and this means researchers can use tropical geometry to study and understand all those possible evolutionary paths.
So it's like using tropical linear spaces to map out evolution.
It is, yeah.
To figure out the most likely paths that happened.
Exactly. It's like having a roadmap.
To the history of life.
Yeah, it's a really powerful tool.
And this is just one example.
Yeah, tropical linear spaces are being used in other fields too.
Like what?
Things like optimization.
Right.
Coding theory, even economics.
That's incredible.
Yeah, they're very versatile.
Now, we can't talk about linear spaces without talking about matrices.
True.
Those are like the backbone of linear algebra.
They are.
Do matrices change in the tropical world too?
Absolutely. Tropical matrices.
Tropical matrix.
They have entries from the tropical semiring.
Right.
And they're super important in tropical linear algebra.
Okay.
We can add and multiply them, but of course we follow the rules of tropical arithmetic.
So we're adding and multiplying matrices, but with that tropical twist.
Exactly.
Does that mean things like rank and determinant still exist?
They do.
In the tropical world?
Yeah, but they can behave quite differently. For example, figuring out the rank of a tropical matrix is a lot more subtle.
More subtle.
Yeah, there are actually a few different ways to define tropical rank.
Really?
Each one with its own advantages and disadvantages.
So even these familiar concepts
Yeah.
get more complex in the tropical world.
They do.
What about the determinant? Does that change too?
The tropical determinant is calculated using tropical addition and multiplication. So the formula is different from the classical determinant.
Okay.
And just like with rank, there are different ways to define and interpret it.
So it's not just a direct translation from classical math.
No, it's not.
It's like reinventing these concepts
You're thinking them.
for the tropical world.
Exactly.
It's so cool.
And this has actually led to some really interesting connections.
Like what?
Well, remember eigenvalues and eigenvectors?
Yeah, those are important.
They're fundamental in linear algebra.
Right.
They also have tropical counterparts.
No way.
Yeah, and they give us new ways to analyze linear systems tropically.
Tropical eigenvalues and eigenvectors. What do those even mean?
Well, in classical linear algebra, eigenvalues tell us how a vector is stretched or shrunk.
By a transformation, right?
Right, but tropical eigenvalues often represent something more concrete. Like maybe the minimum average cost of traveling through a cycle in a network.
Interesting.
So we're not just thinking about abstract transformations anymore.
Right.
We're thinking about real-world applications.
Optimization, efficiency.
Exactly.
It's like tropical linear algebra gives us this tangible interpretation.
It does.
Of these abstract ideas.
And the tropical eigenvectors.
Yeah.
They show us the directions in the tropical space where this minimum cost is achieved.
So they point us towards the best solutions.
Exactly.
Wow, this is mind-blowing.
It is.
It's amazing how these tropical versions give us a whole new understanding of how linear systems work.
Yeah, it's a powerful way to look at things.
This has been an incredible journey.
It has.
I've learned so much.
Me too.
Tropical arithmetic.
Yeah.
It's got these unusual operations, these amazing visuals. It's really made me rethink what math can be.
The great thing about tropical mathematics is that it connects so many different areas.
Like what?
Abstract algebra, geometry, even things like computer science and biology.
It's like this new lens to see the world through.
Exactly.
And it helps us discover all these hidden connections. So as we wrap up our deep dive into tropical arithmetic, I'm left feeling this sense of wonder at how vast and amazing the world of math really is.
It is. And remember, this is just the beginning.
The beginning.
There's so much more to explore in tropical mathematics.
I can't wait.
Me neither.
Well, thank you, everyone, for joining us on this exploration of tropical arithmetic.
Yeah, thanks for listening.
We hope you've enjoyed it and maybe even feel inspired to learn more.
Definitely.